So we said in a previous video that gradient descent doesn't work very well if different columns in the data set have different orders of magnitude. And so one way to fix that is by scaling it before you do any kind of attempt to do gradient descent on the data. So what are the ways to scale the data? So I've just picked a few here. There are others. So this is sort of the most natural one. So this is sort of like if you imagine that x is kind of normally distributed, then this will convert it into a standard normal distribution that has a mean 0 and variance 1. So what this is actually saying is a little bit non-obvious, because x is a vector, and so this is vector subtraction because each column has a different mean. So you need to get that mean from the entire, big capital X, not just from the little x. So like the big matrix X, each column has its own mean, and each column has its own standard deviation as well. So that's why the little sigma here has a bar over it. It's because this is sort of column-wise standard deviation that is computed from the big X. So let's do it in Python here. So maybe we can make this a little bit bigger. Oh no. So x could be equal to np dot arange. What should we do? Like, I don't know, 5 by 5, and then the shape 5, 5. So let's see what that thing looks like. Looks like that. All right, and so in NumPy, everything has to do with broadcasting and axes and stuff like that. So let's print x so that we have it there to look at. But let's also print np.mean x. Okay, so that turned out to be a single number. That's not really what I want, because I want the mean of each respective column, not just the mean of every number in the matrix. So I tell it that by telling it that I'm interested in what's happening on axis 0, and now I get the mean for every respective column. So okay, great. So now I'll define that. Mu is equal to np.mean of x along that axis. Now, wouldn't it be nice if I wrote this, then it automatically did sort of the natural thing, which is to respectively divide each column by the associated average, and that's actually what it does. So it divides the first column by 10. You can see that where 10 was, I divided by 10 and got 1. And so other similar things have happened. So 11 was the average in the second column, so that became 1. And now all of there's no absolute limit to how big or small these numbers can be. All we know is that they all have every column has mean 0, and every column has we haven't changed we haven't done anything about the standard deviation. In fact, what you want to do is subtraction with mu. Sorry, little brain hiccup. So what did that do? You can see that just selected, that subtracted the corresponding, so 11 got subtracted from this column, 12 got subtracted from that column, 13 got subtracted from that column, and you can see it looks very standard, right? Okay, so there's that. And so now let's do the part about sigma. So sigma is np dot standard deviation of x on the 0 axis. So let's just look at that. So this is for the original data. It turns out that the standard deviation in each column is 7. That makes sense because you're just going up by 5s in every column. So in every column, the numbers all differ by 5. So it makes sense that they would all have the same standard deviation. So what if you divide x by the standard deviation? So now every number should have been divided by something like 7. And you can see that, that's what happened. All right. And you can do both things at the same time to complete this kind of standardization. So now the mean is 0 and the variance in each column is 1. And in this case, it actually turns the entire matrix into something that's pretty uninteresting. Okay, so that is that's the theory. Now let's try to do this on some actual data, and when we do, we'll run into some issues. So here I'm loading something called the bike sharing data set. You can download it here if you want to. This has to do with City Bike in New York City. And the idea is you get this information about the temperature and the weather and whether or not it's a holiday or a work day and some other information, the air temperature, the humidity, the wind speed. And then the thing that you're supposed to predict is how many people used City Bike on that day. So there are 3 things that you could use for a target. You have to choose one. So this last one is the total. This one is the registered users, and these are just the casual users. So this is a regression problem. And the goal is to predict how many people were riding City Bike based on the weather and other information. So I start here. I load up that data, and I use the I think I use as a target. What does y turn out to be? Oh yeah, so I have y casual, y registered, and y total. Okay, so I don't. You can see here I scale the. Let me just take this out. I was adding extra. I was doing a little feature engineering there, but let's leave that out, and we'll just use the data matrix. And here I'm doing some scaling. I don't want to show you that function because I want you to write it yourself. But here in the comments, there's a clue as to what's happening here. So sigma is x along axis 0, just like before. Now, it shouldn't be the case that in real data, the standard deviation in a column is ever 0, because that means that the column is just constantly one value. But in practice, it does happen, and in particular, it happens for the bias column. You know, the bias column is all 1s. So that naturally has standard deviation 0. And you have to check for that. And here I replace all the 0 standard deviations with 1. Why do I do that? That's because the computer doesn't like dividing by 0. It makes it angry. And then if you do feature engineering like this, what I do here is I add the products of all the different columns. So when I do that, sometimes that introduces columns that are constantly 0 or 1. So ideally data shouldn't have constant columns. You know, if you're doing a serious application, you should take those out, but I'm just fooling around here. They were just kind of annoying. So you can get rid of all those 0s by doing this. And so there's something else is you don't want to clobber your bias column when you make the mean 0 in the mean 0 in each column. So you actually don't want the mean to be 0 in the bias column. You want the mean to be 1 because you want everything in the bias column to be 1. So my 0th column is my bias column, so I make sure that I actually subtract 0 from that. And then this is a broadcast operation like we talked about before. So here's where I do the scaling, and I'll explain why there's this repetition in a second. But what do we do? So for the target, I decide to use the total, and then I get all of these W's. So one of them is linear regression from the normal equations. That's what NE stands for, normal equations. And then I get one from gradient descent. And then I get one from stochastic gradient descent. And for this one, I use 100,000 iterations and the smaller eta. And then I get my predictions, and I print out how successful they are. This is going to go down because I took out the this line about adding squares. So let's run it and see what happens. So they all perform about the same. So they all have an R2 score of about 0.8, which is a really decent score. So the algorithm is working. For stochastic gradient descent, you can see that it's off by a little bit, but this is 79.9. It's pretty close. So they're all basically the same. So now let's see what happens if I don't scale the data. It starts telling me that crazy things happened. Oh, weird. Stochastic gradient descent actually still works pretty well. But you can see that gradient descent doesn't work at all. It returns not a number. And so it blew up because the data wasn't scaled, basically. So I'll put the scaling back in. And this is a little bit off topic, but since we're fooling around with this, let's see what happens. This stochastic gradient descent was a case where I had to mess around with eta a little bit. If you use a, it was not converging for eta equals 0.1. Yeah, so now you can see that, and this stochastic gradient descent, I got not a number. It failed to converge, and in fact it exploded into something bizarre because the learning rate was not small enough. The professor's not smart enough. The learning rate's not small enough. Okay, but otherwise it all works fine. So there are other things you can do that are sort of similar. One of them is called mean normalization. So I put max with a bar over it because, you know, that's the max in every respective column. This is the min in every respective column. So this is like totally a vector thing that's happening here. And so when you do this, the mean is 0, and this puts all values between -1 and 1. So up here, they could theoretically go as high. You know, there's no bound on how big the or small the numbers can be. It's just unlikely that they're very far from their mean because their variance is 1 and their mean is 0, so they're probably small. But with mean normalization, they're guaranteed to be small. And then another thing you might do, which for these other two, you had to get mu and sigma from the big data set. But now you can just, you can always normalize a vector just based on the information that it contains. So this one you can draw a nice, all of them you can draw sort of a decent picture of what they do, but for these, you know, if you have, if you do unit vector normalization, here's the data out here. So what that does is project everything down onto a unit circle. So this becomes this, and this becomes this, and this becomes this, and this becomes this. So this transformation just puts all the data on the unit circle in 2 dimensions, and it'll be the unit sphere in higher dimensions. Apparently this is useful for image manipulation. So you can play with those and implement them and try different things. So we have one thing left to explain, which is when I wrote my scalar function, it has this weird form where it takes x and then x. That's because really I wrote it so that I could do this. You know, you split the data set into a training part and a testing part. Okay. So when you scale the data, you have to you can't, like that, the mu values that you get, those, all that you're allowed to see is the training values, not the testing values. So whatever mu you compute for the purposes of scaling, that can only come from looking at the training data, and the sigma can only come from looking at the training data. If you also use the test data to compute those numbers, then you're peaking at the test data, and extracting information from it that's going to make your performance measures an unreliable predictor of the actual performance of your algorithm, because you've been stealing data from the test set, and it might improve your oh, oops, I just wrote xtrain twice. It might unfairly improve your estimate of the reliability of your algorithm out of sample. So the way the scaler actually has to work is you do this stuff like I described here, except you get this value mu only from the training set, and you get this value sigma only from the training set. Then you apply this transformation to the training set, and then so here this would be xtrain. Then using the same mu and sigma that you got from the training set, you would also normalize or scale the test set. So it would be like this. All right, and that's all. So just when you do your scaling, be sure that the parameters that you use to do the scaling only come from the test data. If they come from the train data too, I said it exactly backwards. The parameters should only come from the training data. If they come from the test data, then you'll get an optimistic estimate of the performance of your machine. All right, that's it. I'm going to stop this.